Great. Well, I'm really honored to be speaking here today. I guess today I'm going to be talking about, as you said, log concavity of matroid H vectors. This is joint work with Andrew Berget at Western Washington University and Dennis Tseng, who's now at DE Shaw. Okay, so there's a bunch of words in the title. There's like log concavity and matroid and like H vector, and I guess I should explain all those. So first of all, what is a matroid? Well, for the purposes of this talk, we're going to take a collection of vectors inside some vector space. We're going to say this vector space has dimension r. So if I have a collection of vectors in a vector space, then we're going to define the matroid to be all R element subsets of the indexing set such that the vectors indexed by A form a basis of V. Okay, so there are like two extremes. If like all the vectors are 0, then none of the R element subsets form a basis. And if they're all generic, then all R element subsets form a basis. And somewhere in between, there's some interesting combinatorics. So it is what it is. Okay, so let's see an example of this. So I'm going to take some vectors. Let's take V0 and V1 to be along the z-axis. Let's take V2 and V3 to be along the y-axis. Let's take V4 and V5 to be along the x-axis. So this is going to be inside, I don't know, r to the 3. Okay, so what is the matroid? Well, we have to take all of these triples of vectors which form a basis. So there's 0, 2, 4, 0, 2, 5, 0, 3, 4, 0, 3, 5, 1, 2, 4, and 1, 2, 5, and 1, 3, 4, and 1, 3, 5. Okay. So these 8 triplets, which are all the transversals of the 2-element sets 0, 1, 2, 3, and 4, 5, these form the matroid. And given these 3-element subsets, what we can do is we can form a natural simplicial complex where these are the facets of the simplicial complex. In other words, we're going to take vertices 0, 1, 2, 3, 4, and 5, and we're going to join every triple together that forms a basis, and we're going to like take that triangle, and we're going to fit 8 triangles together and see what we get. So let's see what triangles we have. So we have a bunch of triangles involving 0, so 0, 2, 4, 0, 2, 5, we have 0, 3, 5, we have 0, 3, 4, we have 1, 2, 4, we have 1, 2, 5, we have 1, 3, 5, and we have 1, 3, 4. Okay, so if you put all these facets together, you get the boundary of an octahedron. Boundary of an octahedron. Okay, and this simplicial complex is called the independence complex of the matroid because the faces, so the lower dimensional faces like the edges and the vertices, these are the independent subsets. Independent subsets. And when I say independent, I mean like linearly independent, because every linearly independent subset of these vectors is a subset of some basis, because you can always extend a linearly independent subset to a whole basis. Okay, so we have this independence complex, and we have this nice simplicial complex, and associated to the simplicial complex are a number of nice combinatorial invariants. The easiest one would be the F vector. So the F vector is a very straightforward construction. We're going to put the number of 0-dimensional faces here. We're going to put the number of 1-dimensional faces here, and we're going to put the number of 2-dimensional faces here. Okay, 0, 1, and 2. Okay, so let's fill these numbers in. So how many zero-dimensional faces are there? There's 6, and I guess this is negative one-dimensional. The empty set is that linearly independent, I guess. Okay, so there's 6 zero-dimensional faces, the vertices. Looks like there are 12 edges of this octahedron, and if I can count correctly, there are 8 facets. Okay. So this f vector is just a generating function for the independent sets of the matroid counted by their size. So this is a very nice matroid invariant, and it's also a very natural invariant to associate to a simplicial complex, and we put it together into a polynomial because we have nothing better to do. All right. So the f vector is very natural, but what has even more relevance to the geometry of simplicial complexes is the h vector. So the h vector is what you get when I substitute in t minus 1 into the f vector. So this is, I guess I should call this h of t, which is f of t minus 1. And this is going to be t cubed plus 3t squared plus 3t plus 1. Very suspicious. This turns out to be t plus 2 cubed. So this turned out to be t plus 1 cubed. Great. So these numbers, h0, h1, h2, and h3, this forms the h vector. Now, why is the h vector important? Well, there's this ring that you can construct from a simplicial complex called the Stanley-Reisner ring, and this turns out to be the numerator of the Hilbert-Poincaré series for that ring. But I won't go into that now because it's not, important for the for what I have to say. Anyway, so around 1971, Dawson made the following conjecture. Now, who's Dawson? He's a matroid theorist. A lot of people made a lot of conjectures about a lot of matroid sequences, and the ones that really stood the test of time were the ones that said certain sequences were log-concave. So Dawson had a conjecture that this sequence is log-concave. Now, what does log-concave mean? Log-concave means that if I square any element in the sequence, this is at least the product of the 2 adjacent elements. And the reason it's called log-concavity is because it's equivalent to the concavity of the logarithm of the sequence. So, so Dawson conjectured this. And there was also conjecture for the f vector and some other simplicial complexes associated to matroids. This turns out to be strictly stronger than maybe a more natural thing that you'd want to know, which is the log concavity of this sequence. So this log concavity formally implies this log concavity because of this very silly relationship and some algebra you can do. It turns out if you plug in t plus 1 into something where the coefficients are log concave, you get something where the coefficients are actually strictly log concave. So it's even better than log concave. Okay, so Dawson had this conjecture. And we can see it's true in this example, like 3 squared is at least 3 times 1, 3 squared is at least 3 times 1. And he did it for like 100 other matroids and it was true, so maybe it's always true. And only recently do we have the technology to actually solve these types of problems. And so I guess I should say what the theorem statement is. So Andy Berget, myself, and Dennis Tseng, and independently Ardila, Denham, and Huh show the following theorem that this is true. So the H vector is a log concave sequence. But moreover, so we had 2 completely different ways of establishing this. Ardila, Denham, and Huh's method also establishes log concavity of a different sequence associated to matroids that we can't access. But our work is we use simpler methods, but we're actually able to get a strengthening of the log concavity of this sequence. What we can actually show is if I take this quantity, which is non-negative, I can actually lower bound it by something that is positive. And this quantity I can lower bound it by is the following, hi minus 1, which doesn't manifestly look positive, but I want to make a little bit of a note on this. So this this improvement, as it were, it looks like sometimes it can be negative and sometimes it can be positive, but because we established the log concavity of the sequence, what the sequence looks like is it goes up, 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 and then it kind of like stabilizes at the top potentially, and then goes down, 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 down. So it's unimodal. So in the range where it's going up and up and up, the sequence is strictly increasing, so you get an improvement because this is positive when you have them all strictly increasing. Similarly, on the downhill, they're all strictly decreasing, and it's again positive. So we have an improvement over here, we have an improvement over here, and over in this middle bit, both sides are 0. Both sides are 0. So if you have 3 consecutive terms, obviously I can't really get an improvement on like a number squared minus that same number times itself. Like, how am I going to improve that lower bound of 0? You get 0. So this improves the H vector log concavity because it, in all these ranges, it's improving the log concavity. And this is actually sharp in a number of cases. So there are H vector sequences that actually satisfy this, that don't satisfy, that actually attain equality here in non-trivial places. So this seems like to be the morally correct, sharper inequality. And this basically establishes that this H vector sequence is strictly log concave, except when it plateaus at the top, which it can also do. So, it is what it is. Okay, so what is this strategy that we have for establishing log concavity? Well, the log concavity strategy, goes through an important tool in convex geometry called mixed volumes, and a very famous inequality relating to mixed volumes. So to set this up, suppose I have some polytopes P1 through Pk in R to the n. Then the volume of T1 P1 plus T2 P2, and I'll explain what it means to add polytopes together, Tk Pk. So I want to look at what this volume is. Now, what does this mean? So these are just scaling. So I'm taking the T1 scaled copy of P1, the T2 scaled copy of P2, etc. What do I mean by adding? I literally mean set addition. So you take every point in the first polytope, every point in the second polytope, you add them together, and you completely disregard the multiplicities. And this seems like a very weird thing to do, to disregard the multiplicities, but it turns out that this is a very natural operation on convex bodies, and actually essentially makes the polytopes form a semi-ring, and then a lot of the interesting algebraic objects that you can create from polytopes are obtained by taking this ring and formally adding negatives to it. So addition actually works very well, and that's very surprising because the definition seems kind of ridiculous. But anyway, so we have this volume, and what can we say about it? Well, you might think that this is kind of a scary quantity because it might depend on like the combinatorics of the polytopes and the sizes of these t's, so it might be like some horrible like piecewise thing. But actually, this is very nice. This is a polynomial of degree n, polynomial of degree n, and it's homogeneous polynomial of degree n. I guess it's an easy sanity check that this has to be the case. And we can write it out. So because it's homogeneous of degree n, if I take all sequences A1 through AN that add up to N, with all of these A's being non-negative, there's going to be some coefficient times T1 to the A1, T2 to the A2, through Tn to the An, and because I want these numbers to be sufficiently correctly normalized, we're going to divide by this. AK, sorry, this is TK, AK factorial. Okay, so there's some expansion as a polynomial, and these numbers here are called the mixed volumes. So what are the essential features of this mixed volumes? Well, for example, if I take M0, 0, N0, 0, this is just the volume of Pi, where this is in the ith position. So you have the volumes are a special case of the mixed volumes. But additionally, so these kind of like interpolate between between volumes. So the volumes are a special case, and these things kind of interpolate between the volumes. And the relevant fact that we're going to use is the Alexandrov-Fenchel inequality. Alexandrov-Fenchel inequality, which says that the assignment of a sequence that adds up to n to the logarithm of this quantity, a k, is concave. So this is a concave function of the indexing sequence. So you get a lot of log-concave sequences by looking in the domain where this adds up to n and taking lines. So if I restrict to any line, you get a log-concave sequence. So lots of log-concave sequences coming out of this inequality. And how should we think of this inequality? Like, what is any intuition for why you should expect this to be true? Well, there's a famous, so let me tell you like the moral reason why this is true. This is basically a refinement of what's called the Pracopalander inequality, which says if I have a convex body, so here's a convex body. I didn't draw it very well because it's not convex, so let me draw it a little better so it is convex. So I take a convex body and I slice it with parallel hyperplanes. Then the volume of the slice as a function of translation distance is log concave. So this is actually a very general feature of probability distributions in general. This taking the volumes of slices corresponds to taking a probability. You should think of this like convex body as being like a probability distribution for a point in space. And taking these slices is the same as saying I project this probability distribution onto some perpendicular line. And you want to know if I, and the Pracopalander inequality says if I start with a log concave probability distribution and I take marginals, which corresponds to doing a projection, then the resulting probability distribution is log concave. So this is an extremely special case of the Alexandrov-Fenchel inequality. You can choose some polytopes. You can rig it so that the log concavity of this slice function is exactly recovered by the Alexandrov-Fenchel inequality. So that's just a nice piece of information to know. Right. So we want to do this. So this was actually known since like the 80s. So in the 80s, Richard Stanley, and let's say the 80s to now. So this was a long period of time, maybe like 30 years. Richard Stanley at MIT did this like a million times and got lots of log concavity results. Log log-concavity results. Like lots and lots and lots of log-concavity results. And for like many interesting combinatorial sequences that people had thought were log-concave, he chose the polytopes, he got the sequence. He chose the polytopes, he got the sequence. And it was just very surprising how you could keep choosing polytopes and keep getting interesting sequences. So for example, let me give you a silly example of this. Let's say we want to show that the binomial coefficients are log-concave. Then what you can do is you can use the Alexandrov-Fenchel inequality, and I'll tell you what polytopes to take. You take your first polytope to be the standard simplex, which I'm going to write like this. So I'm going to take one-dimensional higher space, but intersected with the sum equals 1 hyperplane. So this is just the convex hull of all standard unit vectors. And I'll take P2 to be its negation. So it's going to be negative P1, which I guess I can also write as a slice of this cube. This is just like a translation of the negation of this. So you can think if I have like a cube and I take the sum equals 1 slice and the sum equals 2 slice, like in 3 dimensions, then the 2 slice, that triangle is negative of the triangle in the first slice. So if I take these two, then these are the mixed volumes of these polytopes appropriately normalized. So this is mn0 all the way through m0n. So you get the log concavity of the binomial coefficients. So you can get binomial coefficients, but you can also get a lot of other interesting sequences coming out of this. Right, but this was too weak, it turns out, to establish the log concavity of any sequences associated to matroids. So people tried very hard and got nowhere in establishing any log concavity of any sequences associated to matroids at all, which is kind of annoying because we have this really powerful tool that has so many possible inputs to it, and just no one can figure out what to do. And then it turns out that the reason is because this tool is slightly too weak, and we need to improve the tool by just the tiniest fraction, and then we're going to be able to access the log concavity of matroid sequences. So to do this, we're going to venture into something called tropical Hodge theory, which sounds crazy because it has like tropical and Hodge in the title, but this is just a very basic combinatorial refinement of the Alexandrov-Fenchel inequality, like a very basic, very minor improvement to the Alexandrov-Fenchel inequality. Okay. So let me tell you what it is. So first I need to take these polytopes that I said addition behave nicely, and you can like scale polytopes and add them. It turns out this like makes a ring, and if you formally negate polytopes, this is a very nice ring. And I want to access this ring in a way which is more useful for log concavity questions. So that there is a ring called the Polytope Algebra, which is you formally consider polytopes where you like you can add 2 polytopes and scale, and subtraction is formal. And there's some like there's a bunch of theory associated to that. I'm going to work with a slightly different presentation as the tropical fan ring. So the tropical fan ring. Okay, and we're going to take all of our fans to be inside n-dimensional space. So I'm going to fix n forever. So this is the n-dimensional tropical fan ring that I'm going to be constructing. Okay, so first of all, what is a fan? So we're going to make this real basic. A fan is a union of cones, like infinite cones. Cone, I don't mean like you truncated and so sorry, like an infinite cone with apex at 0. Weighted by real numbers. Okay, so let me give you an example of such a cone of a fan. I can take root 2, 1, 1. All right, that's a fan. You just wait these. So in this case, I'm drawing it in r to the 2. So my cones are just like rays extending out to infinity. And this would be a one-dimensional fan. So you can have a fan of any dimension. You can have a zero-dimensional fan, which would just be some weight associated to 0. You can have a one-dimensional fan, which is like this. I could also have a two-dimensional fan, which would be assigning weights to like these things. So there's like a lot of different dimensions of fans and n dimensions. They go from dimension 0 through dimension n. So the tropical fan ring is made up of certain what are called balanced fans. And I'll get back in a moment to what being balanced means. There's some condition on these numbers that I'm going to shortly explain. So these are the elements. So certain balanced fans. How do we add these fans? We take a fan, and we take another fan, and we add the weights. Add the weights. So for example, if I had another fan that had like 1 here and like 3 here, then this ray would get updated to root 2 plus 1. This new ray would have 3 on it, and these two would still have 1 on it. So you literally just add them in the most obvious possible way, just as like weighted subsets of space. And now how do you multiply fans? So if I have fan 1 times fan 2. So assuming they're sufficiently transverse, all you do is intersect every cone from the first fan with every cone from the second fan, and the weights multiply. Weights multiply if F1 and F2 are sufficiently transverse. All the cones intersect as you would expect given their dimensions. But if it's not transverse, then you're like, all right, well, I can make a transverse intersection by intersecting my first fan with a slight perturbation of my second fan. So maybe I'll say, like you add epsilon, but then this isn't a fan because it's not a union of cones. So we have to rescale it so it becomes a fan. Whoop. So I have to rescale it a little bit so it becomes a fan. So I take the limit as t goes to 0 of this. And the weights multiply. Weights multiply. So basically, if the two fans didn't intersect transversely, you translate one a little bit, you do the intersection, and then you're like, all right, this looks like a fan if I like zoom out really far, so that's the fan you get. And okay, maybe there's like some like technical condition on how the weights multiply, but this is the tropical fan ring for the purposes of this talk. Very simple ring. And how at all does this relate to the mixed volumes we were talking about before? Well, the way they relate is if I give you a polytope, I can associate a fan. And the fan I'm going to associate to a polytope is the codimension 1 part of the normal fan of P weighted by edge length. That sounds complicated. Let's see what a normal fan is. So what a normal fan is if I give you a polytope, so here's my polytope, take a point inside, and you draw all the normal vectors to the facets. So in this case, I drew all the normal vectors to the facets. And then the fan is like there's like 2-dimensional cones, and there's 1-dimensional cones, and a 0-dimensional cone. In general, there's going to be like n-dimensional cones which surround the vertices, n minus 1-dimensional cones which cut the edges, etc., all the way down. And these like glue together to form a very nice cone complex of cones. And And so we weighted by edge length. This is root 2, I guess. This is 1. This is 1. Oh, look, it's the same fan that I drew before. Okay. So what is this weird balancing condition I was saying? Well, I'm just going to say it in this context. The balancing condition is a condition that's that these fans associated to the polytope satisfy, and at least in this specific case for like two-dimensional polytopes, I mean this generalizes to higher dimensions, but let me just say it here. The condition is going to be that the sum of the vectors is 0. So here I claim that if I add root 2 of this direction, 1 of this direction, and 1 of this direction, you get 0. Now, why is that the case? Well, here's a kind of cheeky reason. If I fill this triangle with air, then these vectors are the forces on each of the sides of the triangle. So this is the net force on this triangle applied by the air inside the triangle, which has to be 0. So if you think about how that proof works, you're like bumping a bunch of tiny air molecules together. This is actually just like Stokes' theorem, or this is just a consequence of Stokes' theorem, that these vectors add up to 0. So there's a higher dimensional generalization of that, and that's the balancing condition. Right. So okay. So the polytope gets this codimensional 1 part of the normal fan, and what's very nice is that the kth power of the polytope gets the codimension k part of the normal fan. Normal fan of P weighted by k face volume. So this is a surprising fact that if I assign to my polytope the codimension 1 part, and then I use this multiplication rule k times, then you recover all of the volumes of all the subsequent k dimensional faces by this simple algebraic operation. So this fan actually encodes all of the relevant properties of the polytope's volume. And in particular, if I take the top power, you recover the volume of the polytope times the trivial fan, which is this. And this is so you recover the trivial 0-dimensional fan times the volume of your polytope. This is just the natural conclusion of this. Okay, so this fan comes equipped with this ring equipped with one more piece of data, but it's not really a piece of data. It's just like one more thing it's equipped with, which is the degree map. And the degree map is just going to forget this part of this product, and it's going to spit out this number. So the degree map, when I apply it to the top power of a polytope, gives me the volume of the polytope. And it turns out very formally that okay, so if I take these, if I take the Minkowski sum of 2 polytopes, it corresponds to adding the weights on the normal fan. So this ring encodes Minkowski addition very nicely. And in particular, one consequence of this is that it's just formally is implied that if you take the degree of, so from this result and the fact and how all these things were defined, it turns out that you can formally show that this degree is equal to the mixed volume with these multiplicities of the corresponding polytopes. So this ring perfectly encodes the mixed volumes that we wanted to understand, but in a ring theoretic way. And the fact that they had to be defined in terms of fans, this is just like this is just the way we have to combinatorially encode it. But really, we care about this statement, that when I take the degree of various powers of these polytopes, which add up, so where these exponents add up to n, k equal to n, you recover the mixed volume. Okay. So tropical Hodge theory I'm going to get to what tropical Hodge theory. What is the point of making this ring? Well, it turns out that certain, let's call them magic fans, delta, have the property that, and again, this is the slightest possible generalization of the Alexander-Fenchel inequality, that the assignment that takes a sequence and maps it to the degree of this fan times P1 to the A1, P2 to the A2, all the way to PK to the AK, is log concave. And now I guess these numbers have to add up to the codimension of this fan in order so that this actually becomes a correct degree product. Okay, so certain fans are magic. So what are examples of magic fans? So let's write down examples of magic fans. Examples. Well, the obvious examples would be any product of polytopes in this ring. So just stupidly, if this was a product of polytopes, then this degree being log concave would exactly be saying it would be exactly saying the Alexander-Fenchel inequality. So this isn't very interesting. The more interesting example, and this is the tropical Hodge theory, anything which is the tropicalization of a smooth subvariety. So this has to be smooth. So the tropicalization is some magic thing you can do to a subvariety of a product of C stars. So this is C stars, just C without the origin. So some algebraic varieties are subsets of that. And there's a process called tropicalization, which I won't get into. But this tropicalization is a fan which works, which is magic. And this is called tropical Hodge theory. Is establishing which fans are magic. And basically, people knew that fans that come from this procedure have this magic property because it formally follows from a corresponding Hodge theoretic property on these smooth things. And then you can extend that. This map turns out to preserve enough structure that you can show that in the limit it gets the property combinatorially. And those were the only fans that we knew this for. And then what Jun He showed back in 2015 or something, well, He showed a number of things. So in his thesis, what he showed is that there's a very particular fan you can take, which is the tropicalization of some linear subspace. So you just take a linear subspace inside C to the n, and you delete something so it becomes C star to the n. So this turns out to be one of these magic things. And what he showed was if I intersect it with those two simplices that I was talking about before, so P1 to the K, P2 to the R minus K. So P1 and P2 are the simplices from before, which you get by taking this hypercube and intersecting it with this 0, 1 to the n plus 1, intersect the sum being 1, and 0, 1 to the n plus 1, and now the sum is n. So these two simplices, if you take mixed intersections, you get the coefficients of what's called the characteristic polynomial of the dual hyperplane arrangement. And as a special case of this characteristic polynomial, whatever it is the chromatic polynomial of a graph. So Junhe showed the log concavity of the coefficients of the chromatic polynomial of a graph by doing this crazy thing. And he actually showed that these fans also satisfy log concavity even when your matroid, this matroid that we were talking about, so M is for matroid, even when the M doesn't come from a vector configuration. So I didn't tell you this, but not every matroid comes from a vector configuration. They're just the most important ones, or the ones coming from vector configurations. But he famously showed using combinatorics that this fan also satisfies log concavity, even if there's no genuine variety with Hodge theory that you can apply this magical tropicalization to get the result. So hard combinatorics actually showed something very impressive. But that's not important for this talk, that he generalized it. What's important is that he intersected some things and he got some numbers. All right. Great. So I like intersecting things and getting numbers. So what the strategy was for us was, it turns out that there are actually some very natural things to intersect with the Bergman fan that come from geometry. I'm not going to go like where the geometry comes from. It comes from ultimately the fact that where this linear subspace comes from. But the natural things that you'd want to intersect with this thing, it turns out, are hypersimplices. So this would be a very good thing to intersect with. Now, what are hypersimplices? So hypersimplices are a very silly generalization of these two things, where you take the cube and you intersect it with a different slice. Equals I, and this is called the ith hypersimplex. So June managed to intersect the first and the last hypersimplex in various combinations with the matroid, and he got this nice sequence. And when me and Andy and Dennis were starting out, we knew that people wanted to understand the intersection with hypersimplices for certain geometric reasons, and we wanted to know what the intersections were. If I just shoved in a bunch of hypersimplices into this formula, maybe you get a nice sequence. And the emboldening thing about this is that hypersimplices, so here's like the key fact which makes this like not a fool's errand. So hypersimplices have the property that they're SN invariant. So like if I permute the coordinates, the hypersimplex remains the same. So this degree, when I intersect it with various hypersimplices, this is always going to be a matroid invariant, and that's not going to depend on the ordering of the underlying ground set, because these things are invariant under the SN action. So we automatically get matroid invariance, and we get log concavity. So we were excited, and we're like, all right, let's jump on this train and find some matroid invariants that are log concave. And it turned out that we found some important matroid invariants that were log concave, which is nice. Okay, so what is the combinatorics of these hypersimplices? Well, to understand them, you have to go through what are called Eulerian polynomials. So Eulerian polynomials are these polynomials that were created that encode the number of permutations. So let's make a definition. Let's say EI R equals the number of permutations of SR with exactly I descents. So for example, if I list out all permutations of three elements, then the descents are when the next number is smaller than the previous number. So it's like here, 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 and here. So this has 0 descents, 1 descent, 1 descent, 1 descent, 1 descent, and 2 descents. You can take all these numbers, stick it into a polynomial, which is the third Eulerian polynomial, 1 plus 4t plus t squared. Okay. So these Eulerian polynomials, so there's an A1, an A2, and an A3, and an A4, have some nice properties. The first nice property that I'm going to say is that you have a very nice expression for the ordinary generating function of fixed powers of some number. So if I want to find the ordinary generating function for like fourth powers, I would plug in r equals 4 into this formula, and I get all the fourth powers as coefficients, and this gives a formula for the sum of for the fourth powers weighted by the number you're raising to the fourth power. And the indexing is off by 1, but I was an Euler, I didn't do this. Okay, so you have this nice power series expansion, and here's a more important fact, that the coefficients are the mixed are the volumes. So the coefficients are the volumes of the r-dimensional hypersimplices. So, for example, this is the volume of P13. This is the volume of P23, and this is the volume of P33. So this is so what are these things? Let me just say what they are. So this is a simplex in 3D. P23 is an octahedron, and P33 is just the simplex, but like negated. So these Eulerian polynomials are palindromic because of this. I guess you could also see it from this definition because you can reverse the order of the sequence. But they're also the volumes of these simplices, so of these hypersimplices. So this is a really nice fact. So what's important for us is generalizing this Eulerian polynomial to something called mixed Eulerian polynomials. Now, when someone in combinatorics defines a polynomial, you're like, man, that was kind of crazy. Why did you define that polynomial? But I'm going to write down some nice formulas, and that should post hoc convince you this was a sane thing to do. So let's write down what a r of y is. Okay, so I need a definition. So I'm going to let a 1 through a n. This is going to be the mixed volume for the hypersimplices P1n, P2n, all the way to Pnn. Okay. So I take the n-dimensional hypersimplices, and I'm giving them names, and the name is capital A subscript and all that. Okay. So if I want to write down the rth Eulerian polynomial, it would look like this. 0y plus a 0, 0, 0 r y to the r minus 1. So you would pad with zeros, and this r would like travel through the padding of zeros, and these give you the coefficients. And the reason is that the mixed volume specializes to volume when you take the mixed volume of something repeatedly with itself. So these are the volumes. These are the actual volumes of the corresponding hypersimplices. And what we're going to do is we're going to generalize this slightly. So let's say I have a sequence like this. And let's say that the sequence A1 through AK, this adds up to something which is greater than the number of numbers in the sequence. That's going to be the condition, and it's going to be the condition so that this thing I'm about to write down makes sense. What we're going to do is we're going to pad with the number of zeros for this to make sense. So like, let's say this is R in this case. So we're going to pad with zeros on either end so that the number of numbers is equal to, I guess here, this had to add up to n for this to make sense. So we pad with zeros. And we just pad with the sequence with zeros. A1, AK, Y to the whatever. Okay. So this is going to be the mixed Eulerian polynomial. And I want to like post hoc justify that this is a reasonable polynomial to study. And I'll do that by writing down a very nice formula. AK of Y is equal to, well, I'm going to write down a very similar formula to the one that was written down for the Eulerian polynomial. Okay, so this is the ordinary generating function for this, up to this denominator. So this is just a direct generalization of what happened for the Eulerian polynomial, which is what happens when the sequence is just the single number r. Then like all these terms disappear, and this becomes an r, and you get back the Eulerian polynomial. So this is a nice polynomial, and this is a nice sequence and nice properties. And this is, I guess, a new way of packaging mixed Eulerian numbers. Previously, no one had packaged it like this, and no one had observed this. But recently, a lot of people simultaneously started observing this immediately after we did this, and now, there's a flurry of work looking at what these polynomials are. So I guess the moral is to understand the mixed Eulerian numbers. You can like take a very nice power series, and then you can extract some coefficients and use that to determine the mixed Eulerian numbers, but not the mixed Eulerian numbers individually, but packaged together into a polynomial. So it turns out to be easier to calculate the mixed Eulerian numbers if you package together its like cyclic shifts. Then if you package together shifts, then it is to evaluate an individual mixed Eulerian number. Okay, so right. So what is the okay? So if I miss left, I have to tell you, I guess, what the result that we have is. So let's say that I take this Bergman fan that was used by Junha. So this is called the Bergman fan, by the way, if you want to look that up. Bergman fan. And I want to understand what happens when I intersect it with some product of these hypersimplices. So P1 to the A1 all the way through PK to the AK. And here I'm writing PI to be the hypersimplex. So I want to understand what this mixed intersection is, because I would really, really, really like to get log concavity of some interesting sequences. So what we found is if you package together these intersections with some shift, so I'm taking these shifted sequences of hypersimplices, just like in the definition of this mixed Eulerian polynomial. And I take the ordinary generating function of this. So the sequence on the top is fixed, and I'm taking the generating function with respect to this shift. This is equal to, what is this equal to? Well, this actually factorizes, believe it or not. This factorizes into two parts. This factorizes into this mixed Eulerian polynomial that we were talking about times the H polynomial that I was talking about. So you get a factorization. I think it might actually be the H polynomial of the dual of the matroid. It doesn't matter. You can take the matroid dual to recover the other one. Right. So these mixed intersections give this lovely factorization. And where this factorization comes from is that if I take this product without the Bergman fan, so here I guess this would be like if I said the degree of this is equal to this. So this is the numerical phenomenon that we found. But this comes from a very nice combinatorial expansion for this these mixed products of these p's, where this doesn't necessarily add up to n. So if it added up to n, we'd get the mixed Eulerian polynomial. But if it adds up to less than n, then it turns out it factorizes a1 through ak of y times some polynomial in the tropical fan ring. And then this, when you intersect with Bergman fan, gives this H vector that you're looking for. So because we have all these intersection numbers, we can play around with these indices, and ultimately we ended up getting the strengthening of the log-concavity by choosing these exponents very judiciously. This is very interesting. So there's like a universal weighted fan. So this is some polynomial in T in the tropical fan ring. So that if in order to extract the H vector of a matroid, I intersect it with the corresponding Bergman fan. So this is like some universal H vector that like encodes all the H vectors of all possible matroids. And this has a very nice expansion if you read our paper. It's like it's like the simplest possible class you could write down in the tropical fan ring. And it has this like wonderful property that it encodes all these H vectors. So this is how we showed it. And I guess that's it because it's 9 o'clock.